Good afternoon. Thank you very much for the introduction. As presented, my name is Jeannette. I'm working at Adaptive Simulation, which is a spin-off company led by the research group of Professor Johann Hoffmann at the KTH Royal Institute of Technology. The vision of adaptive simulation is to make accurate CFD simulation accessible, not only for engineers and researchers, but also for a broader group of users. In this talk, I would like to show some results of benchmark simulation we conducted for one of our applications where we assess the flow dynamic in urban area. This is the outline of my talk. First, I would like to explain why urban simulations are interesting and important. It's connected to the previous talk. Thank you very much. Then I would like to present mathematical and the numerical methods we apply. I would like to give an overview about the automated pathway which we established in our company, which we called Ingrid Cloud. Then I will show benchmark results which we conducted, and I would like to conclude my talk with a summary. Here on the left, this image shows one of the benchmarks. This is a volume rendering of the velocity of one of the benchmarks. This is an actual urban area of the city Niigata. So within urban wind simulations, CFD can be applied for various purposes. For the architects, when they build a new building, it is very important to know how the wind feels for the pedestrian. There are different existing pedestrian comfort criteria, and basically they measure how often the magnitude of the velocity is exceeding a specific threshold during 1 year. On the left-hand side, you see the Science Tower in Kista. This is located north of Stockholm. By calculating the pressure on the building and also analyzing the streamlines or the velocity field behind the building, we can optimize the building and also optimize the planning of the urban area around the building. While having the information about the velocity field, we can also find locations for example, wind turbines to generate locally energy, as you can see exemplified in this picture to the right. So we model the wind in the urban area using incompressible Navier-Stokes equations. For the numerical discretization, we use Galerkin finite element method. We have a tetrahedral unstructured mesh. For the functions, we use linear piecewise continuous in space and time. The problem is time dependent. And for advancing in time, we use Craig-Nicholson. As you know, the problem is convection dominated, and to fulfill the LBB condition, we need to stabilize our system where we use a least square stabilization. We had a previous talk in the morning by Margarita. She talked about the same method. So this is the resulting discretization of our variational problem. You have the momentum, the continuity, and the stabilization terms. For the inflow, we interpolate the benchmark data. For the outflow, we set pressure to 0. And for modeling the turbulence, we use an implicit LES. One of the key elements of our research is to use mesh adaptivity. For the associate adjoint problem of the Navier-Stokes, it can be shown that if you have an interesting quantity m, it could be, for example, drag, we can show that the error in this quantity of interest can be estimated by the computed residual in the momentum, continuity, and stabilization terms. And we use these error indicators to find the elements which we want to refine such that the error in the quantity is reduced. This is the adaptive algorithm which we use. Massi yesterday presented a great illustration of the algorithm. So in the first step, we solve the velocity and the pressure field for the primal problem. Then we solve the associated dual problem with the quantity of interest. We look if we have convergence in the quantity of interest, as I said, for example, in drag. If we have achieved convergence, then we stop. If not, then we bisect a certain percentage of the elements which have the highest contribution to the error. For the benchmarks, I will show later on, we had a percentage between 10 to 15%. This slide shows an illustration how the mesh adaptivity algorithm refines the mesh. On the first row, you see the initial mesh and its velocity field to the left. This mesh has a volume size of about 500,000 vertices. Then we applied the algorithm I just described several times. The second level, I think I achieved with 8 iterations, and the last one after 10 to 12 iterations. You can see how the mesh is refined in the area where interesting dynamics are happening. So this is the wake, and for example here where the flow separates by hitting the edge of the building. Now, how does it work, the automated pathway? We exemplify it by the Urban Wind Comfort app. So when a user access our web interface, she can upload an STL file of the urban model. She sets the inflow direction and its magnitude and choose a resolution. And the level of resolution will define how many iterations the solver will run. Very simple. The only request is that the STL model is complete. As soon as this is done, an automated script is run to embed this city into a semi-sphere, and a volume mesh is created. This volume mesh is then uploaded to a remote supercomputer. We use Hazelhand in Stuttgart. This is a Cray machine. We use the software Dolphin 0.9. This is a branch of the Phoenix platform, which we developed at Adaptive Simulation. This is a CPU code, which has the linear scaling up to 40,000 cores. While running the numerical simulation, we have also the possibility to visualize in situ, as presented by Mr. Onishi. We use the LibSim, and so based on visit. After the simulation run, we create again an automated script is run to create an automated report, which is then uploaded to the web interface and accessible for the user. The report creates a movie based on the time-dependent velocity field, and also calculate a pedestrian comfort. Now let's look at the benchmark results which we conducted to validate our CFD simulations. These benchmarks are set up by the Architecture Institute of Japan. Their goal was to validate CFD simulations applied to pedestrian wind environments around buildings. There are several benchmarks with various complexities. We choose 3 cases. Case 1, or also called Case E. This is a single high-rise building, which you can see here on the left-hand side. Second case is a high-rise building among city blocks. You can see a picture of the wind tunnel experiment here, also called Case D. And then Case E, this is an actual urban area of the city Niigata. Case E or Case 3, you can see here. The measurements which were provided by the Architecture Institute were wind tunnel measurements or on-site measured data. So let's have a look at Case A. This is the simple block. We have the setup here. We have the computational domain. You can see how the mesh is refined in the wake. For this case, we have measurement points in 3 different planes, 2 parallel to the floor on different heights, and 1 in the direction of the wind, as you can see in the figure to the left. In these measurement points, we measured the magnitude of our simulation of the velocity and compared it to the measurements in the wind tunnel. Blue are the CFD, our simulations, and red are the measurements in the wind tunnel. We have very good agreement, and as expected, the difficult domain to capture is of course behind the building. Then in this figure, there are all the measurement points and compared to the magnitude of the velocity. Here we plotted the measurements against the simulation data. We observed that most of the points have a less deviation than 10%. 10% are indicated by the dashed lines. We also, in this table, we calculated the Pearson correlation. If you have a value of 1, then it means a perfect matching between your data and the measurements. While we are refining the mesh, we converge to a value of 0.94, which is very satisfying. So we have really good agreement for case A. Then how about case D? This is the high-rise building among the city blocks. Again, you have the setup, you have the domain. In this case, the measurement points are located around the high-rise building and on the pedestrian level, because this was the interesting level for the architects where the people are walking. Again, the correlation, the magnitude in the different measurement points, we refined until a mesh of 3 millions. And here we lose a little bit of accuracy, but still very satisfying, we think. We achieve a value of 0.86. The last case, this is case E, as I said, of the city Niigata. Niigata lies a little bit north of Tokyo. Here again, the measurement points are located on pedestrian level around these 3 buildings, because they wanted to know how the velocity is influenced by building this high-rise building. Again, magnitude in different measurement points, correlation. Here, again, we lose a little bit of accuracy. We converge to a value of 0.75. For all the cases, case A, D, and E, we observe by reaching a mesh of size 2, 2.5, 3, we converge. So based on these benchmark measurements, we conclude that our automated pathway for assessing the flow dynamic in urban area, we could establish such an automated pathway and with satisfying accuracy. The correlation lies between 0.75 and 0.95, and we want to know more precisely why we're losing accuracy, because now 0.95 is really, really good, but why do we lose complexity, the accuracy with rising complexity? One reason could be that because we have time-dependent solution, but the quantity we measure is a mean value, so maybe we have to run a little bit longer. This could be one of the reasons. Our key elements of the research is mesh adaptivity. We have control over the error and also using HPC. One thing we are doing now, we are implementing different pedestrian comfort criteria, because depending on the country, they're using different criteria. We wanted to make it accessible internationally. One thing we want to model, and it's not included yet, are trees. We want to model them as porous media. One thing, it's topology. In the discussion with architects, for them it's very important to have topology. In the moment we require from the architects that everything is on a flat ground. And of course, we're going to improve the interface and report based on dialogue with non-CFD experts. It's not that easy. Some things we expect, what they don't see or we do see. I wanted to show a video, but the techniques are not working. But this is one of the automated in situ visualization we create. It is also a movie, and I take the chance to take it as a teaser. You can go into the website and you see how it moves. Thank you very much.